Hello everyone, today I will tell you how to pick the right compaction strategy and how that in turn can boost the performance of your database. You know, if you pick the wrong compaction strategy, that can definitely kill the performance of your database. So you don't want to do that, right? I am Rafael Carvalho, and I worked on a couple of nice projects in my life. One of them was SysLinux and also OSV, which is a unikernel for the cloud, C Star, which is the heart of ScyllaDB, and ScyllaDB, which is the best database in the world. The agenda for today, I will explain the concepts behind OSM3, what's compaction, why is it needed, the trade-offs, which is about the trade-offs between read and write and space, the different compaction strategies that we have available at ScyllaDB, when you should, how to pick the correct strategy based on your workload needs. One of the additional features we have in ICS, which is the incremental compaction strategy, and also I will explore the time window compaction strategy, common pitfalls you might bump into when using and how to avoid them. What's LSM3 compaction? First, let's understand how the write path in LSM3 storage works. The updates to your database are inserted into a memory table, which we know internally as a mem table. The data is always sorted according to a token, which is like a hashed value derived from the partition key. And those same updates are also written into the commit log for durability. Memory is a limited resource. So those mem tables have to be periodically flushed into a new sorted file, which we know as SS table. Similarly, the SS tables are also sorted, and SS table means sorted string table. And the SS table are there to make it easy to search and merge data in the process that we know as compaction. Those random writes in the mem table are turned into sequential writes at the moment we flush the mem tables. So you can think like batching writes and turning random writes into sequential writes. After a while, we are going to have many separate SS tables, and those different SS tables that you have accumulated may contain redundant data, like old and new values of the same cell or different rows in the same partition. The problem with that is that by having redundant data, you're wasting disk space and also adding read amplification, which the reason for that is that you have to read more data because you have redundant data, so you have to read both the old and the new cell, compact them, and return like the latest version of the data you want to read. This problem of read amplification, the accumulation of SS tables, is mitigated by a Bloom filter, which is a probabilistic data structure. It's like a technique to mitigate this problem that LSM trees have. So these probabilistic data structures allow us to filter out SS tables that certainly don't have the data you want to read. So it reduces the read amplification in the read path. Compaction is about reading several SS tables that potentially have redundant data and creates a single output file that contains the data, the redundant data merged, so you only preserve the most recent information. Merging those SS tables together is an efficient process, and the reason for that is that all the files are sorted, so we can apply a KA way merge algorithm, which is like you're iterating through the sorted data in each file, combining them, and outputting the most recent information. So as you can see, we merged two files together and we wrote the output into a new larger file. And when the compaction process ends, we replace the input file by the output one, allowing the disk space of the input SS table to be released. And that's without the incremental compaction approach that comes later with ICS that we have in ScyllaDB. This technique is very old. We know from it was published in 1996, but we have a reference to this technique back in the 70s in a paper called Differential Files. The reason for LSM3 is that we wanted to have high write performance, especially in this new era of database where you want to ingest lots of information into your database. And also the information you write into the database to be immediately readable, and you have reasonable performance with the techniques that come on top of LSM3 like Bloom filter I just explained. So this is the very important part of the presentation. You may ask yourself, which compaction strategy I should use in my tables? And this is a very 1 million question because the compaction strategy you use have a large influence in the performance of your storage engine. And the goal of the compaction strategy is to reshape the SS tables. And today, I'm going to look at the good and bad properties of each compaction strategy, so you'll be able to know which strategy to use based on the workload of your tables. So the goal of this strategy is low amplification. You want to make sure that your queries will avoid having to read many SS tables, and also that the overwritten, deleted, and you also want to avoid that overwritten, deleted, and expired data stays on disk for a long time, which causes read amplification, and avoids also excessive temporary disk space, which increase the cost for you to maintain your database. Because if the space amplification is high, it means that you need more spare disk space in order for your database to work. And it's also very important to avoid compacting the same data over and over again, because that reduces the write throughputs. And by reducing the write throughput, you need to scale up. You need to scale out your cluster, and that increases cost. Both of them, all amplification factors are bad in this sense. They increase cost for you to maintain your database. So read, write, and space amplification, you have to make a choice. There is no perfect compaction strategy which is good for every single use case. It's about trade-offs. It's impossible to decrease read, write, and space amplification all at once. For example, we have side-tiered compaction strategy. It optimizes for write, but it sacrifices read and space. It introduced a new problem, which is read and space. And leveled compaction strategy came in later in order to fix this problem, but it sacrificed write performance. So if you look at this three-dimensional efficiency space, which represents the trade-offs, you're going to be able to see that given compaction strategy is going to be located at a particular place, and it can't cover all the edges of this space. There are trade-offs, and you have to choose. So it always starts with side-tiered compaction strategy. It has efficient write performance, bad space amplification. You need more disk space available in order to allow that high space amplification. It also slows the process of garbage collection, because with space amplification, it could happen that you have redundant data across the levels in the OLS entry. And to fix the read and space, level compaction is introduced, and but it caused the write amplification. So size tiered, it has several compelling properties. It's the default compaction strategy in Cassandra and ScyllaDB. In ScyllaDB, actually ICS, which is like size tiered 2.0, with several advantages over size tiered, and I'm going to talk more about that later. So essentially, how it works, how size tiered works. The idea is that it waits for similar sized SS tables to accumulate in a particular level. For example, in the first level after a mem table, and we are going to wait for those SS tables to accumulate. And once they accumulate, we start the compaction process, which is going to compact the data, the redundant data, and on completion, it's going to create an output SS table, which is the combination of all the data in the input SS tables. So as you can see, the output is moved into the next level. And that's essentially how it works. And in turn, when the SS tables accumulate in the next level, then the same process happens, and the output is the combination of the input data, and the output is not going to contain redundant data. The write amplification is log n, which means that a given piece of data is going to have to travel to be rewritten once per level. So, for example, if you wrote a data, it's going to move into the next level, and in the next compaction, it's going to be rewritten again until it reaches the last level. So the write amplification is very, very good, which is why we say it's optimized for writes. The read amplification, not so good, but the Bloom filter, the probabilistic data structure, allow the read amplification problem to be mitigated. And one of the biggest problems with size tiered is that if you continue to update the same partition, you end up with many overwrites. It's said that the storage is most often the primary bottleneck when using flash SSDs at many companies. So it's very important that you make good use of the space available, because there is a storage density is very important for reducing costs. And one of the problems with size tiered is definitely the space amplification, especially with overwrites, with workloads that are overwrite heavy. And later in time, there came level compaction strategy, which promised to fix this problem, but introduced the write amplification problem. So it's not very good for our use cases. Essentially, it breaks the large SS tables into fixed size pieces, and you, instead of having like the tiers inside the tiered compaction strategy, you have levels where adjacent levels, for example, level 1 is 10 times bigger than level 0, and so on. So the fan out, like the size ratio between levels, is what we call the fan out, and that's very important also to reduce further the write amplification, which is already a big problem in level compaction. So the level compaction is intended to fix the space amplification problem, but at the cost of writes. So this is how it works. So we have the SS tables divided into levels. All the SS tables are fixed in size. We use a default size which is smaller than 1 gigabyte. To be precise, 160 megabytes each SS table. And as you can see, each level is 10 times bigger than the previous level. Level 0 is treated especially, but you can see that pattern with level 1 onwards. So level 2 is 10 times bigger than level 1. And by doing that, we guarantee the very small space amplification, but the levels are going to be compacted always with one another. It doesn't allow accumulation of data like it happens in ScyllaDB. So level 0 is merged into 1. So we pick data from when the size of level 1 hits the upper bound. Then we decided to pick SS table from level 1 and promote into level 2 and so on. As you can see, we never write into like a JSON into a new SS table. I mean, actually we write into a new SS table, but we don't. We always take data from the next level such that each level will not contain redundant data. So that's an invariant level compaction strategy tries to keep. It tries to maintain this fact that each level won't have redundant data. The level 1 spends roughly 10% of the keys, level 2 1% of the keys. So when compaction kicks in, we are going to pick one SS table spanning roughly 10%, and we are going to find the 10 overlapping SS tables in level 2 and so on. It's always the excess. If a level exceeds its limit, then we promote into the next. So it wants to achieve space amplification of 1.1, 10%. The space amplification comes in two species. One of them is the temporary space used during compaction. The reason for that is that we can just delete the input data after compaction completes, because there could be reads that are consuming data from the input files. And the second is the redundant data, and that's what level compaction strategy tries to do. The read amplification is great. That's because you're going to have a single SS table at each level that contains the key you want to read. And the worst case is if the leveled compaction cannot keep up with the write rate. So it's not very suitable for if the table has a very high write rate. So it could happen that most of the data will be kept in level 0 because the strategy has to switch to tiered mode in order to keep up with the amount of data being written. So if you're ingesting lots of data, the database will switch automatically to tiered mode in order to keep up with the write rates. So that's one of the things, that's the biggest problem. It rewrites the same data many times, and that's what causes the write amplification problem. So here I'm going to show some examples, some comparisons between them. And in ScyllaDB, at some point you need twice the disk space. That's why there was a very old recommendation of leaving half of your disk space available for compaction, because it could take half of the disk space. And if you don't do that, it could happen that the node runs out of space. In leveled mode, in leveled compaction, you don't have that. But on the other hand, you need more I/O for compaction, because the same data is being rewritten much more times. Here is we can clearly see the disk usages during compactions. The height of this spike depends on the size of the SS tables being compacted. So in ScyllaDB, this spike is much higher than in leveled compaction. And the reason for that is that a leveled compaction breaks those large SS tables into fixed fixed size fragments. And there is also the overwrite workloads, and that's where ScyllaDB is definitely not good at. It may have a version of the key in every single SS table, and as a result, the amount of space amplification can go very high. And that's where incremental compaction is born. It tries to fix the space amplification problem that we had with ScyllaDB without having the right amplification problem that plagues leveled compaction. So the idea is that you bring that feature, that property of leveled compaction, where you break those large SS tables into pieces, which allows compaction to work on a subset of the data at a time rather than having to keep the whole input data opened until compaction is over. So the space amplification is much lower than in ScyllaDB, and it's very similar to leveled compaction strategy. The overwrite is still a worst case, but we are going to see that we have an incremental compaction gained another feature which allows you to use it instead of leveled compaction strategy and not suffer with the overwrite problem, with the space amplification problem during overwrites. The write amplification is essentially the same as ScyllaDB, and the read amplification is also the same without SAJ, which is the feature I'm going to talk about. So you can clearly see the benefits if you compare the space usage between ScyllaDB and incremental compaction. And the reason, and you can ask yourself, is it enough? And it is not. We also wanted to go on and fix the overwrite problem, and not essentially we want the ICS compaction strategy to suit not only the ScyllaDB users but also users that were using leveled compaction. So we want something that can be used as a replacement for both ScyllaDB and leveled. So this is the space amplification goal. It's like combining properties of both leveled and the tiered compaction, ScyllaDB compaction strategy. Of course, if you remember the run conjecture, you're gonna remember that we have to make trade-offs. So it's not going to come without a right amplification cost, but we can employ the concept of cross-level compaction and also the size ratio between levels in order to decrease the right amplification cost and still allow the redundant data to be compacted away during compaction. So it effectively helps controlling the space amplification. It's not like an upper bound, it's actually a goal, but we are gonna see in the example that it actually helps controlling the space amplification if you have enough write bandwidth. And this is how you're gonna configure it. We recommend starting with a value of 1.5, meaning that the compaction strategy will be targeting a maximum of 50% of space amplification. But like I said, it's not like the upper bound. If there is no available bandwidth for compaction, it could happen that the space amplification goes beyond that. And it's clear in this graph how the lower the SAJ value, the lower the disk usage is, meaning that it's being able to control the space amplification based on the value you set. Also, ICS has a much more efficient garbage collection. And a Accumulation of tombstone is actually one of the biggest problems in most of OSM3 implementations, as it's very hard to get rid of them in a timely manner. Tombstones are known to cause queries to become slower. That's because of the read amplification. Like I said, OSM3 is not in place update structure, but actually out of place. So deletion is actually a record. You say, I want to delete this data, but you don't actually remove it in place. You actually store the intention to delete the data. So the more tombstones you have, the more work you're gonna have on the read path. And ICS gained a very big improvement in this area, where it's enabled by default. It employs a technique similar to SCJ, but instead of being focused on space, it's actually focused on the expired data. Internally, we estimate the amount of tombstones that can be purged away, and then we trigger compaction by compacting the data in a timely manner to make sure that your reads are not going to suffer which would happen if there are many accumulated tombstones. So SAJ ICS actually now works in order to get rid of those expired tombstones, those intentional deletions, as quick as possible. And there is also time window strategy, which is designed for time series workloads. So if you have time series, I would recommend seriously considering it, because it was designed exactly for that. It groups data of similar age together. It helps, and it takes advantage of how time series applications work. They use mostly TTL, time to live, in all the data. So the time window builds on some assumptions of how time series work, and make sure that the queries, the read performance, and also the expiration of data will be as efficient as possible. And it's very important to remember also the anti-pairs. If you not have every data TTL'd, if you don't specify a TTL with the data you insert into the database, that may be a problem. So the usual recommendation is specifying the default time to live. And there are also some limitations because the data is segregated across windows, like window buckets. The recommendation is to not use tombstones, but rather only rely on TTL. And also, it's also not recommended doing overwrites. But if it turns out that you have to delete like a giant partition, major compaction is going to be needed after that. But major compaction is about rewriting all the data. Rewriting all the data brings a write amplification problem. You can do it once in a while, but if you do that very often, you're going to have a write amplification issue. The disk can wear out very quickly because you're rewriting the data lots of time. And it could also affect the write performance. So that shouldn't be like a usual procedure. It should be rare. It's there. It's available to help if you need it, but it's not. You shouldn't rely on it like part of your daily activity, maintain the database. And a very important recommendation also is to keep the number of windows to a small constant. Our recommendation is 20. Otherwise, you could suffer with read amplification issues and also memory pressure. For example, if your default TTL is 20 days, then you should configure the window size to be 1 day. Our docs teach that very well, how you can configure the window size for when you decide to use time window compaction strategy. And here is the summary of how to pick the right compaction strategy, or better, how not to pick the wrong compaction strategy, because that could definitely kill the performance of your database. So with incremental compaction, which you can see that for write-only workloads, it works as good as size tiered. But the space amplification is definitely better because it doesn't suffer with the space amplification issue. It gained the space amplification Go feature that helps with overwrite intensive workloads. If you have read mostly and few updates, leveled is still the best choice. Like I said, compaction strategies, there is no like a universal strategy. If you remember the trade-offs, there are certain strategies that are going to be better than the other. But incremental compaction tries to close the gap and satisfy most of the workloads by trying to be like a universal strategy. So we actually think that it replaced leveled and size tiered in most of the cases, especially when you have lots of updates. So you can still ingest lots of data. And SAJ kicks in order to remove the redundant data. But for time series, time window strategy is still the best. So you should go with it. So thanks a lot for staying so far and have a nice ScyllaDB Summit. I hope you enjoyed it. Thank you.